Okay, so discrete and continuous is kind of like a weird, like discrete data does not mean like I'll never tell, ooh, like discrete, like, like it means specific points. But we're going to take a couple of notes, we're going to write some stuff down, and then we're going to talk about this. It's not as weird as it looks, okay? So the first thing I want to write down is x value, which is independent, determines the data type. Okay, so the x value, which is my independent variable, determines my data type. Do you need me to move?
Yeah, I
Do you want to sit right there?
can't. Yes, it's
Okay. All right. The x value is also in control of the y value. Okay. And we call it the input variable. Okay. So it is independent, it determines the data type, it's in control of the y value, and it's our input variable. You may notice a lot of words starting with in. That's a good way to remember which one independent is. Independent is input, it's my x, it's in control. So if I can connect input and x, I'm always going to be able to figure out which one's independent. Okay? So why does the independent variable control the y value? So do y'all remember when we talked about functions and we talked about the meat grinder? Did we talk about a meat grinder in here?
Yeah.
Okay, we're like, so if I take a meat grinder, which is like my function machine, and I stick in beef, and it grinds it up, what comes out? Ground beef, right? If I stick in turkey, what comes out? Ground turkey, right? But if I stick in beef, turkey's not going to come out. Because what I put in the machine determines what comes out of it. That's why my x variable controls the y value, because what I decide, so like this question is about ride tickets. If I decide to buy 10 ride tickets, that determines how much I'm going to have to pay. So what I decide for x determines what's going to happen with y. Okay? So this is just an important concept to know. There's one more important concept I want to talk about. Again, we're not going to go too far into this, but let's talk about this ride tickets at a carnival costing $2 each. So this is my slope phrase. So here, let's just put a little line here. So $2 each, let's say ticket. Even though it doesn't say $2, it just says $2 each. We know it's $2 each ticket that we're paying, right? So if I look at this phrase, from this phrase I can figure out x, y, and m. So 75% of my slope-intercept form I can find just from this phrase, okay? So if I rewrite it, so it's $2 each ticket. See how I kind of wrote that almost looking like a fraction? So 2 right here, the number is my slope. And you see how I did like something over something? That fraction bar is like, this is actually, we're not writing a fraction, we're writing a ratio, a rate. So we're saying dollars per ticket, dollars each ticket, dollars for every ticket, dollars for one. That bar is my slope word. It's each, every, per, for one. That's what the bar represents, okay? But y is on the top and x is on the bottom. So if I see this, I have $2 per ticket. Slope, x per y. So when I just look at this statement right here, so like, for example, let's say I had, oh, I can't find any paper. Oh my God, this is the whole situation. So let's say I have like 5 chickens per waffle. No, you don't have to, but I'm hungry. Okay, so I would say 5 chickens per waffle. Chickens are my y, number of chickens is y, number of waffles is x. 85 miles per hour. That would be 85 miles per hour. Miles is y, hours is x. Anytime you have one of those phrases, you can write it like this, and then this is my slope. So the number is your slope, but the miles per hour tells you your variables. This matters because in this case they gave me a table, but they're not always going to give me a table with the value, with the x and y filled in. Sometimes I'm going to have to figure that out myself. Okay, so that's all the background information we need. Now let's talk about discrete data. Okay, so we're going to write down descriptions of discrete data and continuous data, and then we're going to figure out how to tell what they are. Okay, so for discrete data, let's write this down. And it's not EET, it's ETE. They mean different things. So discrete is dots, okay, which means my domain and range are a list. Yes, Dr. List. Domain and range are a list. And no parts. Okay? Discrete, dots, domain and range are a list, and parts. Well, if you think about it, we've been talking about domain and range we've been talking about discrete and continuous for a couple of days. We just haven't been calling it that. Because y'all remember when we did these right here? Remember how our graph was dots and our domain and range was a list? Well, look at that. Dots, domain and range is a list. This data is discrete data. We just weren't calling it that. So discrete is when we graph dots. And that means our domain and range is a list. Now for the situation, that means we can't have parts, but I'll talk about what that means in a minute. Now let's talk about what continuous is. Okay, continuous is connected. And my domain and range is an inequality. Yes, parts. Okay. And also it could be all real numbers too. Okay. So what did those look like yesterday? Well, they look like this. Okay? They look like this. We had connected graph, so all of the points are connected. It's connected up. And my domain and range were inequalities. Even this is connected. We had an inequality. And then we had ones like this, where it was connected, and it was all real numbers. So we've been looking at discrete and continuous. We just haven't been calling it that. Because discrete and continuous usually refers to a real-world situation, and so we're going to talk about that right now. There is one phrase. So you see this part here where we says no parts and yes parts? There is a question that you can and will ask that is the only question you need to ask to figure out whether your data is discrete or continuous. We're going to write it right here in the middle. Then the question is, are you ready? It's okay, it happens. Are we ready? If I can find it. It is this. Can I, verb half a x? Can I verb half an x? Sorry, I'm going to use my old useless, whatever, don't judge me. It's all I got. Okay. Can I verb half an x? So this means, so I'm going to fill in the blank with a verb, and I'm going to fill in the blank with the x. Okay? So the question is, can I something half a something? So we're going to talk in this problem about what that means. Okay? All right. You all got that written down? All right. Let's go up here to this example. And I'm not even going to try and spoil it. I'm not going to try and keep it secret. This is a discrete situation. Okay? So if I look at this situation, it says ride tickets at a carnival cost $2 each. Okay, so we've already talked about what our x and y means, and they gave us this. So whenever I have a table, I'm going to label it xy. And what am I going to put over the xy? Doctor. Because Dr. XY is the way I remember this. This helps me know which one's my domain, okay, and my range, and which is x and y, okay? So my independent variable, what is independent variable? It's x. And what does x represent? Domain, but it's, well, actually, but it's my number of tickets, right? And down here, the number of tickets describes the domain. Okay, you're 100% correct about that. All right? So what about my dependent variable? What is my dependent variable? It's the y, which is, so like dollars spent. And what does that represent, the domain or range? Range. Okay? So, now we got to figure out what number of tickets makes sense. So let's think about this. Could I go to the carnival and buy no tickets?
No.
What, I couldn't just walk around eating fried stuff all day? Yeah, I totally could walk around eating fried stuff all day, please. Because I've done it. All right? I've done that because fried stuff is good, except fried butter, fried mayo. I have no explanation for what somebody was thinking, but these things exist. I don't want to talk about it. Okay, if I buy one ride ticket, how much am I going to spend? $2. What if I buy 3 ride tickets? $6. How about 5 ride tickets? 10. What about 8 ride tickets? And what if I buy 10 ride tickets? 20. Now, could I buy more than 10 ride tickets? Totally I could. Could I buy 1,000,000 ride tickets? Yeah, I did some math on that earlier. You actually, I suppose you could, but here's how that works out. Hang on, let me see if I can find it. Yeah, okay, here we go. So if I buy 1,000,000 tickets, and let's say each ride is 3 minutes, okay? That means I need 3 million minutes to ride rides. And when I divide that by 24 hours in a day, that's 125,000 days. Which if I divide that by 365 days in a year, that's 342 years. So, yeah, I suppose I could buy them. First of all, I can't even buy them because I don't have $2 million to buy 1,000,000 ride tickets with. But also, it's like impractical. So when we think about our values, what I always want you to be thinking is, I want you to be thinking up to a reasonable value. Okay, we only can buy them up to a reasonable number of tickets, right? Like I cannot buy, don't get crazy. That's all. Okay, I got to make it a reasonable number of tickets. Okay, so in this case, even though we know we could buy more than 10, let's just go with what we see on our graph. So let's say we could buy up to 10 tickets. So what would be how many tickets could I buy? Somewhere between what and what? Between what? I'm sorry, I think we already decided that I could walk around eating fried stuff, so I'm going to say 0 to 10. Thank you. What about total amount spent? If I buy 0 to 10 tickets, then I have to spend $0 to $20. You see how what I choose for X decides what I get for Y? Okay? So, let's plot these points. Actually, I'm just going to plot every single one of them. So I could buy 0 tickets. I could buy 1 ticket for $2, 2 tickets for $4, 3 tickets for $6, 4 for $8, 5 for $10, 6 for $12, 7 for $14, 8. And I'm just looking at the pattern, honestly. I'm not even really, I can see the pattern here. Okay, so here's my tickets. Are we okay? Okay, so the question now becomes, I have graphed this. Should I connect the points? So the question I ask is, can I verb? What am I doing with these tickets? I'm buying them. So can I buy half a, what's my X? Ticket. Can I buy half a ticket? No. So if I can't buy half a ticket, then I can't connect the points. And if I can't connect the points, then I have dots, I have discrete data, and my domain and range are going to be a list. So do you see how knowing what my data is decides so much? It determines my X value. What my X value is decides whether I have discrete data, discrete or continuous data. It describes what my graph looks like. It describes what my domain and range look like. Don't be looking at your watch. Okay? All right. So it decides so much stuff for me, okay? All right. So this, meaning no, tells me what my domain and range look like. And the why or why not, by asking this question, I already said why or why not, because I can't buy half a ticket, okay? So if I look at my domain and range, look, it's not going to fit over there. So let's write it here, okay? I can buy, and since it's dots, it's got to be a list, right? So it's going to be 0, 1, 2, 3. I'm too lazy to write all that, so I'm going to go dot, 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 10. Now, real quick. If I put 0, 1, 2, 3, dot, 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 and that's it, it's not right, because that's not reasonable, because dot, dot, dot means continue this pattern forever. And I cannot buy 75 million tickets. I simply don't have the time. Okay? But if I say dot, 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 10, that means 0, 1, 2, 3. Hey, continue this pattern till you get to 10. You can. I will accept that answer. Now, on tests, they'll list them all out, but you can totally put that with me. I am not, yeah. So if that's my domain, what's my range got to be? 0, 2, 4, 6, dot, 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 20. Do y'all see it? Hey, focus up here. All right. So what's my rate of change, just out of curiosity? It's 2. Right? Because this is my slope. My slope is my rate of change. So what will be the equation for this? Y equals 2x. I started 0, 0, so it's just y equals 2x. Okay? So do we kind of understand this one? Okay, so now let's look at an example of continuous data. Okay? So for this one, I have a swimming pool that has a volume of 7,500 gallons of water. It's being drained at a rage. That should be rate, not rage. There's no rage here today, okay? It's being drained at a rate of 500 gallons per hour. So where's my slope phrase? At a rate of 500. Oh my God, seriously. Okay, so 500 gallons per hour. Gallons is which one, X or Y? Y is always on top. Hour is X. 500 is my slope. Except 500 is not my slope. What's wrong with that? 500 is... Why is it negative? Because I'm draining the pool, right? I'm not adding more water to the pool. The water in the pool is getting lower. Starts at 7,500 and it drains 500 gallons every hour, okay? So again, you got to think about that. It's minus 500, all right? So what's my independent variable? That's my X, right? Well, that's my number of gallons, right? Wait, what? No, it's number of hours. I'm sorry. My number of hours. My Y is my number of gallons remaining. It's remaining because I'm draining the pool, so we're looking how much water's left in the pool, how much water is still in the pool. Okay, we got time, don't worry. Okay, so what do I start with? Yeah, at 0 hours, so I haven't started draining the pool, I got 7,500 gallons. Do I have enough here to write an equation? Well, I have a y-intercept right here, and I've got the slope right here, so I could say 7,500 minus 500x, or I could say y equals negative 500 plus 7,500. 500x plus 7,500. Either one of those are perfectly wonderful, lovely equations. And why do I want an equation? Because I love my calculator, and I want to put this equation in my calculator. Okay? Because I'm not trying to do all kind of math in my head, y'all. Okay? So I'm going to look at the table of values, right? So if I go up here to 1, I don't care about that. This is going up by 2. So I start at 7,500. After 2 hours, I'm at 6,500, and then 5,500, and then 4,500, 3,500. I'm at 8 hours. 10 hours, I'm at 2,500. This is a long time to drain this pool. 12 hours, I'm at 1,500. 14 hours, I'm at 500. So can I make it all the way to 16? No, because when I get to 15 hours, how much water is in the pool? None. Can I keep draining the pool when there's no water in it? No, okay? So, the lowest I can go is 15. After 15 hours, I got 0 gallons, okay? Now, should I connect the points on this graph? Okay, let's talk about it. The question is, can I drain half an hour? Right? Because hour is my x, drain is my verb. Can I drain half an hour? Yeah, totally. Why not? Right? And if I should connect the points, then my domain and range is inequality. Okay, so I'm going to connect these points. We're running out of time, so go fast. Okay, so I connect these points up. Now, can I go lower than 0 gallons in this pool? No, so I'm kind of boxed in down here. Can I go back in time? Despite all our wishes, we cannot. Also, even if I could go back in time, if the thing only holds 7,500 gallons and I pour more water in it, it's all going to slosh over the sides, and I still only got 7,500 gallons in the pool. Okay, I can't go higher than 7,500 gallons. So, I'm kind of boxed in here, aren't I? All right. So, how many hours can I spend draining this pool? 0 to 15 hours, right? Because I could just be like, look, I can't take it with this pool anymore, just stop draining it, right? Okay. What about y values? Well, okay, if my x values are 0 to 15, that means it's going to look like this, right? My x's are between 0 and 15, and I put or equal to because I could not drain it at all, and I could drain it for 15 straight hours and run out of water, right? What about my range? What are the y values I can use? I could use 0 to what? 7,500, okay, which means my range goes from 0 to 7,500. What's hours, domain, and range? Well, domain is number of hours. Okay, so this one's domain. And remaining gallons is range. What do you guys think about this? Do you think you can do this? Okay, well that's okay. Tonight's homework is 5 problems. Okay, tonight's homework is 5 problems. So on the first of all, the left side of these is almost exactly like what we just did in the homework. And the notes. The right side, see over here it says which letter graph? The first 4 there are graphs. There's 9 graphs. You're only going to use 4 of them. And then the last one you're using the graph to answer the questions. Okay? So that's it.